Hi everyone, my name is Barnabas. The plan for today is to have a brief introduction to regression. We will define what regression is, then discuss what the goal of regression is, what we mean on the optimal regression function, and how to measure the performance of different regression methods. Then we will talk about how to define the consistency and convergence rates of regression methods. Here is my favorite book of statistical machine learning. I love this book and I think you cannot start reading this book early enough. It's really an amazing book. It is called Distribution Free Theory of Non-Parametric Regression by Yerfi et al. This book contains all the details of the proofs, nothing is omitted, nothing is left as an exercise for the reader, and everything you need is in this book. In what follows, we will need a couple of basic properties of density functions and expectations. If you are not familiar with these properties, then please consult with a book that provides a basic introduction to probabilities. The first property we will need is the expectation. If x is a random variable with density p, then the expected value of g of x, where g is a function, is just defined by this integral gx px dx. Sometimes when we have complicated mathematical expressions and we take expectation, it's not always obvious what the random variable is in this expression. To help our understanding, usually I indicate the random variable in the subscript of the expectation operator. Here we showed how to define the expected values with a density function. In the next property, we will show how to reverse it, that is, how to get the probabilities using expected values. Let capital A denote a set. Let this one be a function, the so-called indicator function. This has value 1 when x is in set A and this is 0 otherwise. It's easy to prove that the probability that x is in set A equals the expected value of this indicator function. As a special case of this, we get the next property. Let f and g be two functions. Then the probability that f of x is not g of y equals the expected value of the indicator function of the event that f of x is not g of y. As you can see here, in the subscript I denoted x and y as the two random variables. And we need to take expectation with respect to the joint distribution of these random variables. A famous and very important property is that the expectation operator is linear. It means that for any random variables x and y, it doesn't even matter if they are independent or not. And for any constant non-random quantities c1 and c2, the expected value of c1x plus c2y equals c1 times the expected value of x plus C2 times the expected value of y. The next property we will need is that you can get the conditional density, that is py given x, as the joint density pyx divided by the marginal density px. The following equation shows how to calculate the conditional expectation. Let x and y be two random variables, and let g be an arbitrary function of these two random variables. Then the conditional expectation of gxy given x is nothing else, just this integral here. This integral is integral gxy py given x dy. As you can see, here in the subscript of the expectation operator, we indicate that the random variable is y and we condition on x when we need to calculate the expectation. It is very similar to the normal expectation, but instead of integrating with the joint density pyx, we need to use the conditional density of py given x. This conditional expectation, where we condition on x, will be a function of x, since we integrate out y only, and therefore it is a random variable in x, but it is not random anymore in y. The next equation shows an important property of the conditional expectation. The conditional expectation is also linear, but there are some slight differences on what we mean on this linearity. If we have two random variables, x and y, and we have an expression that's a function of these two random variables, and we need to calculate the conditional expectation of this expression given x, then this x acts as a constant in this conditional expectation. It means that x and any function of x, f of x, can be moved outside from this conditional expectation. Another important property that we will use is the law of total expectation. Given two random variables, x and y with a joint density, and we are also given a function g of x and y, then the expected value of gxy can be decomposed as two expectations. First, we calculate the conditional expectation of y conditioned on x, and after that we calculate the second expectation, where we take expectation with respect to x. So the inner expectation is a conditional expectation with respect to y given x, and the outside expectation is just a normal expectation with respect to x. Before we move on, let's quickly define supervised learning problems, since regression will be a special case of that. The goal of supervised learning is to create a predictor f that can predict the output label of target y from the input variable x. When we create this function f, we want this to have a good performance. We measure this performance with the risk function. We use different risk functions for classification and regression problems. In classification problems, the target variable y is discrete, and the most often used risk function of f is just the probability of error, that is the probability that f of x is not y. In regression problems, The target variable y is continuous, and because of that, we use a different risk function. Most often, we use the mean squared error risk function. This is just the expected value of f of x minus y squared. Let's start focusing on regression problems, which are supervised learning problems where the target or output variable y is continuous. There are lots of different regression problems and applications. Sometimes we use time as the input variable. For example, we can formulate the weather prediction problem as a regression problem where we have to predict the temperature at a future time point. As another application, sometimes we use spatial coordinates as the input variable instead of time. For example, in this task, our goal is to predict contamination levels in some spatial locations in a lake using some sensors placed at other locations in this lake. Now we are ready to define the goal of regression problems. Let x be a d-dimensional random variable and y be a real-valued random variable. More generally, y could be a finite-dimensional random variable, but for us, just to make everything simple in this case, we will just assume that y is a real-valued random variable. Our goal is to find a function f that maps from d-dimensional spaces to the real line such that f of x is a good approximation of y. There could be multiple ways to define what we mean on good approximation, so let's discuss some of them. We define the L2 risk, which is also called the mean squared error risk, as the expected value of f of x minus y squared. It measures that in an average sense, how big is the squared distance between f of x and y. Our goal will be to find a function f that minimizes this, that is where f of x is close to y in this sense. We could have chosen other risk functions as well. A more general risk function is called the LP risk function, where instead of measuring f of x minus y squared, we use f of x minus y absolute value to the power of p, and we take the expected value of this quantity. For different values of p, the optimal regression function can be different as well. We will focus on the L2 risk because the mathematical analysis is simple in this case and the estimator can be computed easier as well. To summarize what we just discussed, let x be a d-dimensional random variable, this is our input, and let y be a real-valued random variable, this is the response or target variable. We assume they have a joint distribution pxy. Our goal is to find a function that minimizes the risk, which is the expected value of f of x minus y squared. The function that achieves this global minimum is the optimal regression function, and we denote this function with m. During this minimization, we consider any kind of function that can map from a d-dimensional space to the space of real numbers, and this expected value can be calculated. There are two major difficulties. The first one is that usually we don't know the joint distribution pxy. In practice, we only have a training set available sampled from this unknown distribution. The second difficulty is that even if we knew the joint distribution pxy, we would need to minimize this risk function over all possible functions f, which is a very difficult optimization problem. Those optimization algorithms that most of you might know, for example, gradient descent and its variants, they operate in finite dimensional vector spaces. Here, however, we need to minimize this quantity in a function space. We need to find that function that globally minimizes this risk. Generally, this is a very difficult optimization problem. However, when we use the L2 risk, we will see that this minimization problem is surprisingly simple. Let's see how the optimal regression function looks like. As we just discussed, our goal is to find the optimal regression function. In other words, we need to find a function that minimizes the mean squared error risk. Our first main theorem claims that this optimal regression function can be found in a closed form. We can also prove that this function is the expected value of y given x. This is great news because we found the globally minimal solution of the risk minimization problem. We don't need to run any gradient descent of any kind in the space of functions. The theorem says that when we use the mean squared error risk, the optimal regression function is always the conditional expectation of y given x. And that's awesome because we solved all regression problems. And we can just go home. All the difficulty left is to calculate this conditional expectation. The problem is that to calculate it, we need to know the conditional distribution of y given x, but in practice we don't know it. In practice, all we know is that we have a training set of x and y instances that are sampled from the joint distribution of x and y. To get some more intuition for regression problems, it can help if we think of the random variable y as a signal component plus noise, where the noise component epsilon is a zero mean noise. It doesn't need to be Gaussian. The signal component is mx, where m can be any kind of function. It's easy to see that in this case again, the optimal regression function is just the signal component mx. And this mx is the expected value of y given x. In what follows, we will prove our first main theorem, which claims that the optimal regression function mx is the expected value of y given x. To prove this theorem, we will need a simple lemma first. Let function m denote the expected value of y given x. Let f be an arbitrary function that maps from a d-dimensional space to the space of real numbers. This lemma claims that the expected value of fx minus mx multiplied by mx minus y is 0. So for any function f, this expectation will be always 0. The proof of this lemma is quite simple. We have two random variables, x and y, and we need to take expectation with respect to the joint distribution of x and y. Because of the law of total expectation, we can rewrite this expression as two expectations. First, we take a conditional expectation of y given x, and then we take the expectation with respect to x. We know that when we condition on x, then in the conditional expectation, any function of x behaves like a constant and can be moved out from the expectation. Because of this fx minus mx term can be moved out. By definition, mx is just the expected value of y given x. Here, this term y after taking the conditional expectation of y given x then just becomes the expectation of y given x. So this term here is 0, and therefore this term here is 0, and because we multiply by 0, then the whole expectation is 0, and this is what we wanted to prove. To prove our main theorem, we will need one more lemma that we call the Pythagorean decomposition. As before, let m be the conditional expectation of y given x, and let f be an arbitrary function. Then this lemma claims that for any function f, the expected value of f of x minus y squared, that is the mean squared error risk of function f, equals the expected value of f of x minus mx squared plus the expected value of mx minus y squared. So this is a bit similar to the Pythagorean theorem, which claims that c squared equals a squared plus b squared in some triangles. The proof of this lemma is quite simple. We need to rewrite the expected value of f of x minus y squared. As a first step, let's just add mx to this expression, and then let's remove it immediately. So we don't change the value, we don't change the right hand side, and the right hand side is still the same as the left hand side. We know that a plus b squared is a squared plus b squared plus 2 times a times b. So this expression here can be expanded as a squared plus b squared plus 2 times a times b. However, in the previous lemma, we just proved that this expression here is 0. So we got that expected value of fx minus y squared is the expected value of fx minus mx squared plus the expected value of mx minus y squared. This is what we needed to prove. Now we are ready to prove our main theorem. As a reminder, we just need to prove that if we want to minimize the mean squared error risk function, that is the expected value of f of x minus y squared, and we want to minimize this expression for all possible functions, then the conditional expectation of y given x will be the function that minimizes this expression. The proof is very simple. By lemma 2, we already know that the risk function can be decomposed as a sum of two terms, the expected value of fx minus mx squared plus the expected value of mx minus y squared. We need to minimize this expression in f. Since the second term doesn't depend on f, then this whole expression will be minimum when f of x equals mx. Since mx is just the expected value of y given x, this completes the proof. From this decomposition, it also follows that for any function f, the risk of f is just the expected value of fx minus mx squared plus the risk of function m, where again m is just the expected value of y given x. This theorem can be illustrated geometrically the following way. Let this be the space of all functions, and let y be a random variable. We want to find a function in the space of all functions that will be the closest to y, that is where the expected value of f of x minus y squared is minimal. From the theorem we just proved, we know that this function m will minimize this distance. And from the Pythagorean decomposition, we also know that the expected value of f of x minus y squared equals the expected value of fx minus mx squared plus the expected value of mx minus y squared. In other words, we can think of function m as an orthogonal projection of y to the space of all functions. So we proved that the conditional expected value of y given x minimizes the mean squared risk. Just as a reminder, the conditional expected value of y given x can be calculated with this integral. So if you want to solve a regression problem, all you need to do is to calculate this conditional expectation. The only difficulty left is that to calculate this conditional expectation, we would need to know the conditional density of y given x. However, often this is not known in practice, and we will need to use our training data to estimate the expected value of y given x. Regression algorithms try to use our training data and then produce a regression function that should be a good approximation of the expected value of y given x. There are many different regression methods, from linear regression and regularized linear regression to nonlinear methods. There are, for example, spline and wavelet-based methods for regression, and recently neural network-based regression methods became very popular too. Parametric methods use the training data to estimate finite many parameters and then use these finite many parameters to create a regression function. Some examples for this are linear regression, polynomial regression, or neural network regression. A major drawback of parametric methods is that they cannot be better than the best function in the assumed parametric class. For example, linear regression methods might produce large error if the true regression function that they want to approximate is not linear. Non-parametric regression methods, however, don't assume that the regression function that we want to approximate can be specified by finite many parameters. Some examples in this group are k-nearest neighbor-based regression methods or the Nadaraya-Watson smoothing kernel method. In what follows, we will formally define the consistency and convergence rates of regression methods. When we use our training data and create an estimated regression function, we want to know how far this is from the optimal regression function. To be able to talk about this, we need to discuss what we mean on how far the true regression function is from the estimated regression function. We need to measure the distance between two functions. Let Dn denote our training set. In this set, we have n training instances. They are xy pairs, that is, we have x1 by 1, x2 by 2, and so on, xn, yn. Let mn x denote the estimated regression function at a location x. This regression function depends on the training data set Dn, so sometimes we also indicate that here. There are multiple ways to measure how far mn is from the true regression function m. For example, we can mention the pointwise error, where we just want to know how far mnx is from the true regression function mx, for some fixed point x in a d-dimensional Euclidean space. Another way to measure the distance of Mn from M is to use the LP error, which is the integral of Mnx minus Mx absolute value to the power of p over a fixed set C. As a special case of this, when p equals 2, is the L2 error. Sometimes we might be interested in the supremum norm error as well. This is also known as the infinity norm error, which is just defined as the supremum of Mnx minus Mx absolute value over a fixed set C. Now we are ready to talk about the L2 risk of the estimator Mnx. Let again Mnx denote any regression estimate using the training data Dn. The risk of Mnx can be defined as the expectation of Mn at the location x minus y squared conditioned on the training data set Dn. In other words, we are given the training data set Dn and we want to calculate the expected value of Mnx minus y squared. In this expected value, x and y are random quantities and we condition on the training set Dn. This conditional expectation will be a function of Dn, and as a result of it, it's a random variable since it depends on the training data set Dn. Let mu denote the density function of random variable x. From lemma 2, we already know that the risk can be decomposed as the sum of these two terms. This decomposition holds for any function f. This lemma didn't use the training data. However, very similarly, using almost the same kind of steps, we can also prove that a similar equation holds when we condition on the training data set Dn. This is the next lemma, the Pythagorean decomposition when we condition on the training data set Dn. This lemma says that the conditional expectation of Mnx minus y squared conditioned on the training data set Dn can be written as the sum of these two terms. These terms are exactly the same as before, except they are conditioned on Dn. However, in the second term, m is not a function of Dn, y is not a function of Dn, therefore here we don't need to condition on Dn. Here, the first term is the conditional expectation of Mnx minus Mx absolute value squared conditioned on the training data set Dn. Here, in this term, we need to take the expectation with respect to the random variable x conditioned on the training data set Dn. So this can be written as an integral of Mnx minus Mx squared, and this multiplied with the density of x, which was just mu x. Since we condition on the training data set Dn, we keep Mnx as a function of the training data set Dn. We don't take expectation with respect to Dn. This expression here is just the mu squared norm of the difference between functions mn and m. Sometimes we just write this decomposition in a shorter form, namely we just use this notation. Since we condition on Dn, this term will be a function of the training data set Dn, and therefore it's a random variable. In this term, the regression function mn also uses the training data set Dn, Therefore, it's also a random variable. However, this last term doesn't depend on the training data set dn, and we take expectation with respect to x and y, and therefore it's a non-random quantity. So we already know that when we are given a training set dn, then the risk of the estimated regression function mn can be decomposed as the sum of these two terms. When we want to find the best regression function using our training data set dn, then we need to minimize this expression in mn. However, the risk is just the sum of these two terms, and the second term doesn't depend on mn, and the first term is indeed minimal when mn is m, that is the conditional expectation of y given x, and therefore this whole expression, the conditional risk of the regression function mn, is minimal when mn is the expected value of y given x. If magically we could set mn to be m, the conditional expectation of y given x, then the risk of it would be just the last term, that is the expected value of mx minus y squared norm. Now we are ready to define the consistency of an estimator. We say that an estimate mn is consistent if its error converges to 0 as the sample size n is increasing to infinity. Based on what kind of stochastic convergence we mean on this, we can talk about weak consistency and strong consistency. Now we are ready to define the consistency of an estimator. We say that an estimate mn is consistent if its error converges to 0 as the sample size n is increasing to infinity. Based on what kind of stochastic convergence we mean on this, we can talk about weak consistency and strong consistency. Let's define the weak consistency first. Let P denote the joint distribution of x and y. We say that the estimator mn is weakly consistent for this distribution P if the mu norm of function mn minus m is getting closer and closer to 0 as we increase the sample size n and is going to infinity. This mu norm is a non-negative quantity. It is also a random variable because it depends on the training set dn. So now we need to discuss what we mean on that a non-negative random variable is converging to 0. Here we say that if the expected value of this non-negative quantity converges to 0 for the distribution P, then the estimator mn is weakly consistent for this distribution P. Similarly, we can also define the strong consistency of an estimator. So let again P denote the joint distribution of x and y. We will study the same quantity as before. This expression here is the squared mu norm of mn minus m. This is a random quantity because it depends on dn. We say that mn is strongly consistent for the joint distribution pxy if this random quantity converges to 0 with probability 1. In other words, the probability that this squared mu norm doesn't converge to 0 is 0. In the previous slides, we defined the weak and strong consistency of an estimator for a distribution P. In many applications, we don't know exactly what that distribution will be, and often we want to create estimators that will be consistent for many different distributions. For example, let this calligraphic P denote the joint distributions of x and y where the expected value of y squared is finite. So this is a set or family of distributions. Based on this, we can define the weak universal consistency and strong universal consistency. We say that an MN estimator is weakly universally consistent for this family of distributions if it's weakly consistent for each member in this set or family of distributions. Similarly, we say that an MN estimator is strongly universally consistent for this family of distributions if it's strongly consistent for each member of this family of distributions. Now that we have defined the consistency of an estimator, we can formally define its convergence rate. Let Mn be a consistent estimator for distribution P. As we have discussed, it means that the expected value of the squared norm of Mn minus m is converging to 0 as we increase the sample size n. Let this quantity, the expected value of the squared mu norm of Mn minus m, be denoted as Rn. The consistency means that Rn is converging to 0. The convergence rate of an estimator measures how quickly this Rn quantity converges to 0. Our goal is to create regression estimators that will be consistent and will have a very fast convergence rate for a large family of distributions. The problem is that if our family of distributions that we consider is too large, then there's a negative theorem which says that for any given Mn estimator, one can always find a difficult distribution Pxy such that even if our estimator is consistent, its convergence rate can be arbitrarily slow. In other words, for any Mn estimator and any convergence rate, if the family of distributions we consider is too large, one can always find a very difficult distribution in that family such that the convergence rate of our algorithm will be slower than that convergence rate that you just specified. To avoid these difficult distributions, we will restrict the family of distributions to a smaller set. For example, we assume that each distribution in this family of distributions has a density function that's p times differentiable. And then our goal is to find the best possible estimator in this family. We define the best possible estimator in this minimax sense. That is, we calculate for any Mn estimator how far that estimator is from M, and then we want to find the most difficult distribution in this family for this Mn estimator. Our goal is to find the best possible estimator that has the best convergence rate for the worst distribution in this distribution family. Later we will see that indeed there are some estimator methods that can find the best estimator in a fixed family of distributions. To be a bit more concrete, let's consider the same family of distributions that we just talked about. That is, let Fp be a set of distributions where each distribution in this family has a density function that's p times differentiable. We can prove that there's a regression estimator whose convergence rate in this family of distributions is big O n to the minus 2p divided by 2p plus d, where d was the dimension of input x and p just shows that the joint density of x and y is p times differentiable. Later we will see that there are estimators that we can construct and can achieve this best convergence rate in this family of distributions. So we will see that we can construct regression estimator Mn star such that for each distribution in this family of distributions, even for the worst one, the convergence rate of Mn star will be always faster than this expression here, where c is just a constant that does not depend on n. As you can see, the larger the p, the faster the convergence rate, and the larger the d, the slower the convergence rate is. So as a summary of what we just discussed today, we defined the goal of regression, we defined the risk function that measures the performance of regression methods, we showed that the optimal regression function can be found as a conditional expectation of y given x. We talked a little bit about parametric and non-parametric estimators, and then we defined the consistency and convergence rates of regression methods. Thank you for your attention.